Hello. So in this episode, we'll discuss the last very important property that we normally assume in the preference relation, and which is the continuity. Okay. So, and we'll use that property and to show that if the preference relation is continuous, and then we can always find a utility function that is representing this continuous preference relation, and that utility function is continuous as well. Okay, so basically we're trying to give this proposition and to prove in two parts, right? So the first part is that we can find such utility function representing this preference relation, and in addition, and we also want to prove that this preference relation, this utility function, it is continuous. Okay, so this comes to the proposition on the textbook of 3.C.1. Okay, so it's saying that suppose that the irrational preference relation, okay, X is continuous. Okay, so then the result is that we can always find, or there is a continuous utility function Ux that represents this preference relation. Okay, so if we can successfully prove this proposition, and then we can use the utility function instead of the preference relation in the analysis of the decision making problems. Okay, good. So okay, so the proof. So the first part would be to show that there is this utility function, right? So the second part will to try to show that this utility function is continuous, right? So basically there are two steps. Okay, good. So now let's try to establish the first result, that there exists some utility function to represent this preference relation. Okay, all right, so for the case, let's say we let this X to be the real numbers which are positive and in dimension of L. Okay, and of course we didn't mention that this preference relation is monotone, but this is already implicitly assumed. Okay, so we should add this monotone here, right? Okay, so this becomes a more complete statement. So, and in monotone preference relation, okay, so we'll use a very intuitive proof. Okay, so here that we're going to show this in a little figure here. Okay, so suppose we have this R2 real numbers with two dimensions. Okay, and those are positive real numbers. So let's have this indifference curve, or this indifference set here, and we have this point X here. Okay, good. So let's draw a diagonal ray, and you could simply draw any rays. Maybe you can draw anything here, or maybe here, but it doesn't matter. Okay, so just for simplicity, we use the diagonal 45-degree line, this ray here, okay, which is easier to show the results. Okay, to just to observe the patterns on the diagram. It doesn't matter if you just draw any rays with any degrees here. Okay, it doesn't matter. Okay, so let's denote this ray as Z. Okay, and this will be 45 degrees. Okay, so in this ray L, so this is the locus of the vectors with all the L-dimensional or here two-dimensional components, right? They equal to each other by this Z. Okay, so this is the ray, diagonal ray that we're going to show this utility. So, and further, we're going to use this little e to denote the L vector or here 2 vector, right? Those elements are all equal to 1. Okay, so e here will be just 1 and 1. Okay, so Z is 45-degree ray. Okay, so then what we have is that, so let's have some non-negative scalar, non-negative real number alpha. So alpha times e, this vector, and then it has to be on this 45-degree ray, right? And it has to be true. So now, okay, so let's suppose, okay, so this is the indifference curve or indifference set, right? So here we restrict this L to be 2, so this will be the R2 space, right? That we normally see. Okay. Good. So after the construction, you observe that this actually we could have a 3-dimensional figure to illustrate the idea of the utility, right? So this is just a 2-dimensional demonstration for the preference itself. But if you want to add one more dimension, which is the utility, then it becomes a 3rd dimension on top of this. Okay, good. So that'll be something later. So here, let's concentrate on this proof. So now we have those tools set up. So now we can see that for every so for every x in L plus R plus L or R plus 2, so we already assume the monotonicity, right? So monotonicity gives us that x has to be weakly better or weakly preferred to 0. Okay, 0 vector. So, and so something has to be better than nothing. Okay, so in this case, because x is always positive in other dimensions, not negative, right? So, and we can also notice that this is a note, and we also note that for any, let's have some alpha upper bar. Okay, so for some alpha value, let's say this alpha upper bar, such that this alpha upper bar times this vector e, it has all dimension greater than those corresponding entries in X. Okay, let's suppose this would be some point here. Okay, so this would be alpha upper bar times e. Okay, so the monotonicity again and the continuity, those two properties together, then can be shown to imply that there is a unique value alpha or alpha x. Okay, so such that this alpha times e is indifferent to x itself. Okay. All right. So let's write it down. So monotonicity and continuity together imply that, and we'll show this later. Okay, so there is a unique value, okay, alpha or alpha x, and that'll be an element in 0 to alpha bar, such that this times the unit times the 1 vector e, and that has to be indifferent to x itself. Okay, so where is this point? So it is exactly this intersection, right, of level of the indifferent set x and the intersection with this 45-degree ray. So this would be alpha xe. Okay, good. Okay, so now we're gonna show this, right? And to show that this scalar, it is exactly this alpha x. Okay. So we're gonna show this implication, or to show this little proof. Okay. So so by the continuity, okay, and we have mentioned that the continuity implies, in the definition of that, we have the upper and lower contour sets. Those two sets are closed, right? Closed sets, including the boundaries. Okay, so that we can approach, or we can converge the limits right on this, right at this indifferent set. Okay, so that all those okay, you remember that if we have continuity, then let's say if this would be an indifferent set, and we could have very small change of this indifference curve, or this indifferent set, all those small slight changes, those are still continuous. Okay, so that would be the continuous continuity for this preference. Okay, so, and it has to have the upper and lower sets, contour sets, to be closed, including the boundary itself, so that we can change those continuously, right? Okay, so the upper and lower contour sets are closed. Okay. All right, so mathematically, and then we could, because those are closed sets, okay, so we could simply change those elements y into something using the alpha and e. Okay, so then let's denote this upper contour set, or some set equivalent to that, okay, using alpha instead of y. Okay, instead of some point, let's use something on this line. Okay, so so let's write it down and explain this further. Okay, so r plus, and this is weakly preferred to x, and similarly we denote alpha minus to be the set that those alphas, and where x is weakly preferred to alpha e. Okay, so those are non-empty and closed. Okay, so why we could change the y's to those alpha e's. Okay, so the underlying intuition of this is that normally we have, let's say, if x is this point. Okay, so we have something, let's say a point was, let's say this ray is here, 45-degree line ray. Okay, so we could simply map, or this would be something in topology, right? So we could simply regard all those y's. Let's say if y is somewhere here, okay, we could always use those points, okay, or this y, maybe this is z, okay, this will be y prime and this is z prime. We could always use y prime to represent this y and z prime to represent this z, okay, and those results here, those results, they should not change. Okay, so we simply lower the dimension here, or we compress this two-dimension space onto this 45-degree ray. Okay, so now we could simply concentrate on this ray, and we can just ignore all the other parts, right? So that becomes easier for us to prove this result. Alternatively, you could just have any other, like, sort of any ray similar to this, right? So those won't change, as we just mentioned before. Okay, good. I hope this will be useful for us to further understand this proof. Okay, good. So now we have those two sort of equivalent in topology. Those are equivalent to have the y's, right? So now we have this alpha e, and those are non-empty and closed sets. Okay, as to represent the upper and lower contour sets. Okay, so and further, we note that by the completeness, we could always compare. Okay, so by completeness, so this would be also a useful assumption. Otherwise, we don't need that, right? So by the completeness of the preference relation, so this upper and lower contour sets together, it should cover the whole space of R plus. Okay, in this case, right? So R plus, it has to be a subset of the A plus union with A minus, right? Okay, good. So then the non-emptiness and closeness. Okay, so and then it's not then. So this is another statement, right? So the non-emptiness and what? And the closedness of those two sets, A plus and A minus, and something else, okay, along with the fact that this R plus, it is connected, okay, and this altogether, it implies, right, we have multiple conditions, imply that the intersection of A plus and A minus, it has to be something other than empty. Okay, so it has to be non-empty. Okay, so this would be pretty trivial to prove this. Okay, if you are interested in this, and you could try to prove this, but this is pretty straightforward. So, and so that would be all the conditions that we need, right? And thus, so there has to be there exists some real number or some scalar alpha such that alpha times e is indifferent to x. Okay. So we have this, you could regard this A plus as upper control set, A minus as lower control set, but this here we simply consider on this Z on this 45-degree array, right? So, and we said that the altogether the union of those sets, they cover the whole space in this two-dimensional positive space in real number here, right? And the intersection of those, it is not empty. Okay. And here we have this alpha e, okay, so which is exactly at this point. Okay, so this would be, and there's only this 1 point of this alpha, right? So that we could use this alpha to, and there's at most one alpha, right? To scale this vector e to be the same length with this x, okay? And that is our utility function, okay? Okay, so now we take this alpha x, okay, so normally we write this as ux, right? So it will be utility function. Okay, so now finally we have our utility function. So that is we can assign a utility value, just some real number, right? Non-negative real number, utility ux, and exactly equal to fx and to every x, right? Okay. Good. So this would be the utility, okay? And further, we wanna we need to check if this utility function it is continuous, right? And that'll be also important in further analysis, right? So if that utility function is continuous, then we could take the and further, if it is not only continuous, but if it is also differentiable, then we could take the derivatives and start to solve the utility maximization problems by taking the first order derivatives and so on and so forth, right? So that would be also a very important properties to check, to prove for now, okay? So, okay, so now we're gonna do that, okay? So we need to further check. Okay, so check two things. Okay, so the first thing is that this utility function, u, it represents a preference relation. Okay, so what does it mean? It means that mathematically, so if we have utility, or if this alpha x greater than or equal to alpha y, and this has to be sufficient and necessary that x is weakly preferred to y. So if and only if x is weakly preferred to y. And we're gonna check the second is that this utility is a continuous function. Okay. And we'll use the definition for a function to be continuous. Okay, so the first will be relatively easy, and it will be just several lines, but the second will be pretty long. Okay, so now let's do the first proof. Okay, so this utility represents the preferences. So this proof exactly is its construction, right? Okay, so mathematically, suppose that let's have alpha x greater than or equal to alpha y. Okay, so we're gonna use monotonicity. Okay, so then the above thing, this implies that alpha x times vector e is weakly preferred than alpha y times e. Okay, and again, because x is indifferent to alpha x e and y indifferent to alpha y e. Okay, so x is by the transitivities, so x is weakly preferred to y. Okay, so we have proved one direction. Okay, and the other direction will be very symmetric to this, right? And suppose we just write the other direction as the condition. Suppose x is weakly preferred to y, then alpha x e is indifferent to x is weakly preferred to y, which is indifferent to alpha y e. So by monotonicity in alpha x is greater than or equal to alpha y, or ux uy, right? Those are the same thing. So okay, so hence or therefore those are necessary and sufficient conditions. Okay, good. All right, so that is very simple, but the continuity will be relatively complicated. Okay, so now let's try to show this, and we will strictly follow the steps on the textbook and try to have some insights and try to understand the proof on the textbook. Okay, good. So the second thing will be the continuity. Okay, so now we're gonna argue that, okay, to show that this alpha or ux is a continuous function, okay, and at all x's. So by definition, okay, mathematically that is for any sequence, we're gonna use the sequence and limit again, right? So for any sequence x n, okay, and from 1 to infinity, with x to be the limit 1 and goes to infinity, that will be the limit of xn. So what we have is this, the limit of this function, the limit of alpha as n goes to infinity, alpha x, and it has to be alpha x. Okay, so it converges to the limit itself. So then in this case, this function is continuous. Okay, so if the limit doesn't equal the value right next to some point in when it tries to converge or tries to approach the limit, if there's some break point, right, then this function is not continuous, right? So for example, if we have some function here, but this would be a empty circle here, but we have this continuous on here. Okay, so this would be a discontinuous, or this function is not continuous, right? So in limit, then if we approach this, we're getting closer, but eventually this limit here, this point is disconnected. Okay, so this is not good and it's not continuous, right? Okay, good. So that's just some example of the continuous function. Okay, so Hence, let's consider just a sequence xn as we mentioned in the definition, and from 1 to infinity, such that the x is the limit of xn. Okay, good. All right, so now we're ready to go. And first, we notice that the sequence alpha xn, so this whole sequence, it has to have a subsequence, a convergent subsequence. Okay. Okay, so now we're going to show this. So by the monotonicity, okay, we'll write this in short, by the monotonicity. So for any positive number epsilon, so alpha x prime lies in a compact subset of R. So compact means it's closed and bounded, right? Subset R plus, okay? And this would be the set from alpha 0 to alpha 1. Okay, it's closed and bounded. Let's change the color. So this is closed and bounded. Okay, good. So the compact set is often seen in the